A, legit or not legit? Taylor.
Not legit.
Why not?
Because HA.
HA.
The alternative hypothesis.
The alternative hypothesis that can talk.
Can't be equal.
Cannot be equal. Very good. So that is very true. So A is frowning face, aka not legitimate, because the alternative cannot be equal to. It must be either greater than, less than, or not equal to. Very good. Part B, Anna, what do you think? Why?
Because H sub 0 is equal to, which is right, and H sub A has the inequality, which is
You are half right. If that was a parameter instead of a statistic, it would be legitimate. But remember, X bars are for sample means. Your parameters must be in terms, or excuse me, your hypothesis must be in terms of parameters. They must be mu's and p's. All right. So B is not legitimate due to the fact that you're using a sample statistic and not a population parameter. Okay. You guys go with that? Miranda, C.
Yeah.
Why?
Because the HO is equal to the other one is not.
Are you using parameters? Okay. What's this parameter represent? What is P? What kind of proportion? Very good. The population proportion. Yep. So very good. It is a legitimate one. All right, Calvin, D.
I'm not sure.
Take a guess.
Yes.
Why? Why did you guess yes and not no?
I mean, it follows the same rules except like the second one doesn't say 0.4, it says 0.6, and I'm not sure.
What do you guys think?
No.
It is not legitimate due to the fact that you just pointed that out. The values must be the same. Okay? So for your alternative and your null, they have to have the same p-value, like the probability or the same. Okay? Does that make sense? Madison, finish it out for us. E.
Not legitimate.
Why?
Because it's the first one is the one that's HO is not equal to, and then HA is equal to.
Is that a problem? Why is it a problem?
Because the HA is supposed to be the one that's, it's not supposed to be equal to, it's HO that's supposed to be equal to.
Very good. Okay, so HO must be equal to. All right, so HO is always going to be the one that you suppose is correct. What kind of example did I give you guys yesterday in the video? Murder trial, right? You say that it's not guilty, okay, and then, so because here's the thing, you suppose that someone is not guilty and you're trying to prove that they are guilty, right? And you have to build evidence. So the more evidence you have, the more likely you're able to say that somebody is guilty versus not guilty, right? Okay. Probability for this is going to be p-value. So we were just talking about that evidence, correct? When we talk about the p-value is, this is the probability that we get from either a z statistic or a t statistic. And assuming that your null hypothesis is true, this is the probability that the test statistic would have a value as extreme or more than what is actually observed. Okay? So assuming that your null hypothesis is true, the probability that the test statistic would have a value as extreme as or more than what is actually observed. Remember our friend Joy from our smelling Parkinson's activity back in the day? This was a day, it was the first day, stats. We did a fun activity. We smelled t-shirts, but they were actually pieces of paper. And then we did it by guessing. Null hypothesis. She was guessing. Alternative. She was not guessing. The probability is how much evidence you have against the null. That null hypothesis was she was guessing. That's over here. So do you guys see anybody else in the class from either second or fourth period that got as many right as Joy by guessing? No. So we know that 0 out of 28 were 11 or what? Or more. As extreme as Joy's guess or more extreme. That's a p-value. It's a rough estimate. In this case, when we did the simulation, but that is in essence, what that statement says on the board. That is a p-value. As extreme, 11, or more, or 12, by chance alone. What's the p-value of observing someone by random chance getting 11 shirts or more correct? 0. See any of our dots over there? No. Does that mean that we have a lot of evidence here to suppose that the null hypothesis is actually not true? Because what did we end up concluding? That Joy was not guessing. Okay? Now, the lower the value of your p-value, the more evidence you have against the null hypothesis. So having that p-value of 0 means that there's a 0% chance that basically you would see somebody getting 11 or more right by random chance. However, the probability, the true probability of that is probably very, very low, but still very low. Okay? So p-value is going to be basically how much evidence do you have against the null hypothesis. Take the murder trial, for instance. Okay? Null hypothesis, you are not guilty. Alternative, you are guilty. What are things that you need to kind of collect in order to prove someone guilty in a murder trial? You need evidence. What about a note saying that I'm going to stab this person? Is that enough evidence to conclude that they murdered that person? What if you had a note and the knife? Is that more evidence? Okay. What if you had a note, a knife, and a dead body? What about a note, a knife, a dead body, and fingerprints of the person who wrote the note on the knife and on the body? There you go. Do you guys see how extreme I got with those examples? I mean, we're thinking about a hypothetical murder trial. This is all hypothetical. There's actually not a dead body in my backyard. I promise. Don't go look. But anyways, what I'm saying is, do you see how those examples got more extreme over time? Yep. Think about that as a p-value, right? Think about that as a p-value, all right? The more evidence you have, the stronger you're like, okay, you could be probably not guilty. Okay, it's not looking good. All right, you're definitely not guilty, right? You definitely not guilty, meaning you're guilty, right? Had to do double negative there. You guys with me there? Okay. The lower that p-value, the more evidence you have, more likely to reject the null hypothesis. Are you with me? Okay. So when you're calculating these p-values, all right, for proportions, you're going to use the normal curve. And you're going to use z-statistics as such, right? So that means you're going to use normal CDF. You guys already know how to do that. Isn't that amazing? Like, you're just translating your knowledge that you already know, and you're going to apply it to something new, which is the hypothesis test. For means, you're going to use the t-distribution, and you're going to use the t-statistic, and you're going to get a t-score. That's something that you don't know how to do, but in the next 5 minutes, when I go through the probabilities, you're going to see how stinking easy it really is. It's the same thing as a normal curve, except it's the t-curve. That's it. All right. Now, when you calculate probabilities by hand on the normal curve or by the t-distribution for a hypothesis test, if you do it by hand and don't use the calculator, spoiler, you're probably going to use the calculator. But if you do it by hand and you have a two-tailed test, that means you got area in both tails. So what you're going to do, and we're going to do an example of it, what you're going to do, find the area in one tail and times it by 2 to count for both tails. Should make a lot of, intuitive sense. Okay? So what we're going to do is we're going to do this example. So first example says we're going to given a right tail test, t-score of 1.6, n equals 20, correct? So take out your calculator, and I'm going to go over to my Smart View. I know I have a right tail test. I have t equals 1.6, n equals 20. Is that correct?
Yeah.
I'm doing it from memory.
Yeah.
Okay. Remember, draw a little curve. Okay, T distributions look like normal distributions, just have more area in tail, correct? Over here at 1.6, that's your t-score, correct? Right tail means you're going to shade it to the right. So you're looking for that area. So the area that I'm actually looking for is the probability that t is greater than 1.6. Do you guys see that? All right. Going to our menu to help calculate probabilities. Second, vars. Normal curve is how we use for when we have z statistic, right? T-score, t-distribution, number 6. Do you guys see number 6? T-CDF. I want you to hit number 6. All right. Compare and contrast. How is this similar to the normal CDF button? Those work the same exact way. What's different? Instead of mean and sigma, right? U and sigma are gone. You replace it with DF. So you got to know the sample size. Do you guys see why you're getting the sample size over here? You need that in order to calculate it. Because remember, your t distribution changes as your sample size changes. The higher the sample, the more it looks like a normal curve. Lower the sample, the less it looks like a normal curve. Still looks normalish, just more area in the tails. All right, so we're going to type in 1.6 for lower bound, because I'm starting at 1.6. I'm going where? Infinity to 10 to the 99th power. Degrees of freedom, I have to do n minus 1. So what is that? All right, calculate this. And what is that probability? 0.063. You guys with me at 0.063? Okay. That's going to be the probability of you observing something as extreme or more extreme by random chance. So that means there's only a 6.3% chance you would see something as extreme or more by random chance. Technically, that's more likely than what Joy did, right? Is that enough evidence? Is that a low enough probability to make you like, something's off? Or do you want more evidence? And if you want more evidence, you need a lower p-value, right? So I want you to think to yourself, is that low enough? Well, we'll test, right? Next one, you have a left tail test with z equals negative 2.4 and n equals 15. So if you're given a z statistic, which curve are you going to use? Normal curve or t distribution? Normal curve. Let's go back over here. You guys already know how to do this, okay? So I'm going to clear out this button here. I have a z of negative 2.4. N equals, does it actually matter what n equals?
No.
Nah, it doesn't. Because remember, I'm going to negative 2.4, and I'm shading to the left of that. Now, the probability is actually much lower. This is not the scale. Disclaimer, right? Not the scale. All right, second bars. Which one are you going to go hit? 2. You guys already know how to rock and roll this. What should I put in first? Negative 10 to the 99th, right? Upper is 2 point.
Negative.
Thank you. Negative 2.4. 0, 1. Enter. 0.0082. So it's a 0.82% chance of seeing something that extreme or more extreme. That low or lower. Extreme doesn't mean that's absolutely higher or lower. Like, it depends on the scenario. It depends on the tail. So here, notice what I said. It's the probability of you observing something negative 2.4 standard deviations below the mean or more extreme than that. More extreme means smaller than that. That's a 0.82% chance. What do you guys think of that? Likely to happen by chance alone? Something's off? Is that enough evidence?
I don't think so.
You want more evidence, Calvin?
Yeah.
I've given you the note, the knife with the blood on it, the body, the fingerprints. You want more evidence?
I don't think that's.
There's intent, there's murder weapon, there's body. What else do you want?
We need confession.
A confession?
That,
Oh boy. You guys are rough. Okay. All right, two-tail test. So this time we have t equals 2.5, n equals 25. So my question is, what curve do you use? Normal curve? T distribution? All right, let's do that. So going back to my calculator, t distribution. So I'm going to just kind of sketch it real fast. Remember, you have area in both tails. So at 2.5, you have area above that. But you also have area on the other tail, which means you have area at negative 2.5 and below that. You guys see how you have area in both tails? Now, here's what we're going to do, folks. You're going to choose your t-score of 2.5, correct? And you're going to shade this to the right. That is half the area. You guys understand that's half your area? Because over here you have another half. So what we're going to do is we're going to do 2 times the probability of t being greater than 2.5. Right, so we're going to double one of the 2 tails. It doesn't matter which tail. You can easily do 2 times the probability of t being less than negative 2.5. And those are the same. I hope you guys see that they're the same. So first thing I'm going to do on my calculator, I'm going to hit the number 2. And why am I hitting the number 2? Because it's 2-tailed test, I have to double whatever probability I find. So now I'm going to hit second bars, and which one am I going to go to if I want to find this probability? 6 for TCDF. 2.5 to infinity. And what was my sample size again? 25. So DF should be 24. All right. So notice that that probability is 0.019. I think it's 6 if I'm not mistaken, correct? Yeah. Oops. Still not good at this racing thing. All right. 0.0197 actually. All right. You guys good with calculating those probabilities? What are these p-values? What are they? What are we calculating? Probabilities. And this probability is the evidence. It's the evidence we're presenting. Generally, you present it to a judge or a jury, right? And they are usually the ones who decide. So how do you decide if you have enough evidence? Well, if you're Calvin, you need everything. You need videotape evidence. You need 4 witness statements, a signed confession, the body, the bloody knife, the fingerprints, the body itself. Is that enough?
Sure.
Sure. Okay, cool. Okay. So who is the judge and who is the jury in the quote-unquote hypothesis test trial? The level of significance. My friends, this is the judge and the jury. This represents the amount of evidence necessary before we begin to doubt that the null hypothesis is true. This is how much evidence is enough evidence to say that null hypothesis is probably false in favor of the alternative. Okay? Now, this is also a probability at which we will reject the null hypothesis given that we say it's true, or assuming that it is true. So this level of significance, you need to understand, is a probability. We denote it by the notation alpha. It's the Greek letter A, alpha. It can be any value you want it to be. So different judges, different juries may require more or less evidence, correct? So here, you can kind of pick your judge or pick your jury, almost, and say how much is enough. Generally, the big 3 are 0.10, 0.05, 0.01. Those are the big 3. However, the most common is 0.05. If in doubt, 0.05 is the amount of evidence you will need. So what you're going to do is you're going to take your evidence, your p-value, and you're going to compare it to the judge and the jury's requirement, and you're going to say, if it's lower than this, you're going to reject HO assuming it's true. If it's not low enough, you're going to fail to reject. Does that make sense? So this is like how much evidence. Now, if it's Calvin, Calvin would be like 0.0001, right? Is everything. All right. You guys good with this? Statistical significance. This is when the p-value is as small or smaller than your level of significance. So this is when you prove that you have enough evidence. So once you prove you have enough evidence, you have what we call statistically significant evidence to conclude. All right? What we're going to do is do one of two things in this class. You're going to either fail to reject the null hypothesis, HO, or you're going to reject the null hypothesis, HO. And that's based on how much evidence you have. So I was already alluding to how you need to use the p-value and how you're going to compare it to the alpha level. All right? If p is greater than your alpha level, the level of significance, you're going to fail to reject HO. You don't have enough evidence. If p is smaller than or equal to that level of significance, which means you have enough evidence or just enough, you have more than or just enough, you're going to reject the null hypothesis and conclude something else. You're going to conclude your alternative, whatever that other alternative is. Does that make sense? Okay. Take this example, for instance. We're going to play a game. The game is called, are you going to reject that hoe? HO. Null hypothesis. Reject that hoe. So remember, this is the key phrase in statistics, guys. When the p is low, you reject the hoe. When the p is low, you're going to reject the hoe. And you guys gotta stop laughing because you guys have dirty minds, okay? I'm talking about the null hypothesis. When the p is low, you're going to reject the null hypothesis. I don't know what you guys are giggling. But remember, we call it HO, H naught, H ho. You kind of, okay. So, we're going to reject the ho or not reject the ho, right? So, at an alpha level of 0.05, would you reject or fail to reject the ho, given the p-value? Remember, what's the big phrase? When the p is low, reject the ho. All right. At 0.05, you have a p-value of 0.03. Is the p low?
Yes.
Reject the ho. Part B, 0.15. Is the p low?
No.
Fail to reject the ho. About 0.45. We're going to fail to reject that ho too. That null hypothesis, I should say. 0.023. When the p is low, reject the ho. All right. Let's just say that you guys are usually never confused about comparing a p-value to an alpha. You usually make the correct decisions. You generally take your p-value. You know what to do with that p-value. Did you guys enjoy our game today? Okay. Here's the facts about the p-value. Again, what is a p-value? You got to know what this is. It's the probability that you will see something as extreme or more extreme by random chance. It is the evidence against the null. The lower it is, the more evidence it is. I want you to think about my murder scenario. How much evidence does the judge or jury need? How much stuff do you need to give them? That's the p-value. All right. Here's some facts about it. This p-value always makes decisions about the null hypothesis. So your p-value always talks about HO, H naught, H sub 0, the null, whatever you want to call it. Remember, large p-value shows support for your null, but never proves it's true. For instance, when you're in that murder trial and you're saying that someone is not guilty versus that they are guilty, does that mean that person is innocent?
No.
Not necessarily. Because what did you do? You had evidence to say either that person is not guilty, you don't have enough evidence, so you say they're not guilty, or you have enough evidence and they... Do you actually know if that person did it or not? No, you don't. That's the same idea. We don't know if that HO, that H naught, that null hypothesis, we don't know if it's true. We're talking about this p-value, and we're saying we have enough evidence to either say we're going to reject it or we're not going to reject it. That's all we know. We're not proving it true. Now, small p-values show support that the null is not true. You guys know the phrase, if the p is low,
Check the mode.
or the hoe gotta go, right? There you go. Whatever you want to do. You never, ever, 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 ever accept the null hypothesis. You never accept the hoe. You're going to do one of three things with the null hypothesis. You're going to reject the hoe. You're going to fail to reject the hoe, but you'll never accept the hoe. Those are the three things you need to know about your null. You reject the null, fail to reject the null, or you don't, and you never accept the null. So, no accepting of the nulls here. Now, sometimes in AP Biology, AP Biology, they like to tell you that you can accept the null. Never accept it. Again, you can never know if a person is really innocent. You just have evidence that they either did the crime and they're guilty of it, or you don't have enough evidence and they are not guilty of the crime. Does that make sense? All right, writing conclusions. You're going to do two things. Number one, you're going to write a statement of decision being made, aka reject HO or fail to reject HO. And you're going to tell us why. You guys see this word linkage here? Linkage. That means you're going to take your p-value and you're going to say it's less than alpha, or you're going to take your p-value and say it's greater than alpha. That is what we call linkage. That is linkage. So basically, you're linking your p-value with your alpha level, your evidence with your significance level. And then you're going to, in the same part, you're going to write a statement of results and context. You're going to conclude HA. You always conclude about the alternative. Okay? So you're going to reject the hoe. So that means you have evidence to support the alternative, because you rejected the null. So the only other hypothesis you have left is the alternative, right? If you fail to reject the null or the hoe, you do not have enough evidence to talk about HA. So either you do have enough evidence to conclude HA, or you do not have enough evidence. One of the two things got to happen. All right, so here's the conclusion and context here. Since the p-value is less than or equal to alpha, we reject HO. Remember, p low, reject the hoe, right? P is low, hoe got to go. There is sufficient evidence for HA. So that's one scenario. What do you guys think the other scenario is going to be as you're writing this down? If it's greater than alpha. All right, and you're basically going to flip that. All right, here is that other statement.